You know that to learn quantum mechanics, you need to learn some mathematics, and linear algebra is one of them. But have you ever thought that why do you need linear algebra and not anything else? What is the deep underlying connection between linear algebra and quantum physics? Is it that you need to master everything about linear algebra to learn quantum physics, or there are some core fundamental concepts which you should master? Even so, the question is why? What are the best books, methods, and learning models that you need to know to learn quantum physics and precisely linear algebra? In this video, you would be learning all those things, and you will come to know that what are the best books that you should pick up for your self-study. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this episode on how to learn linear algebra for quantum mechanics. Now, when we start with the video, I would like to talk about quantum mechanics, and here is a note that I'm not going to talk about the usual quantum mechanics or quantum physics, the superpositions, etc., but something deep. Now, first I would like to answer that what is quantum mechanics? And you all know that it is a fundamental theory in physics that describes the behavior of nature at and below at the scale of atoms. That means it is basically something at a microscopic level. The next question which comes is this: why do we need quantum mechanics? And what we have seen over the passage of time and the evolution of scientific theories, that classical physics at some point of time fails, or you can say it has got a limitation to explain phenomena at the microscopic scale, such as the stability of atoms and the discrete energy levels of electrons and so on. So we need a new theory, we need a new kind of a mathematical formulation which can describe things at the microscopic level, and they can define discrete energy levels of electrons and the strange behavior of particles when we perform what is called the double slit experiment. So we understand what is quantum physics, we know why do we need quantum physics. The next important question is that how does it help us? Is it at all helpful to us, or just we have to read it? So the answer is that yes, it is helpful because it provides a deeper and more accurate understanding of the nature of reality, which is existing at the smallest scales. So this brings us to our next question. So what is the basic job? What is the function, or what actually the quantum mechanics or the mathematics of quantum mechanics as a whole, what it does? That is coming up in the next part of the video. What is the basic job of quantum mechanics? First, obviously, that any scientific or mathematical model would be able to predict what is called a system. And in this case, we call it predicts a quantum system. That means it provides a kind of a mathematical framework for describing the states and dynamics of a system, which goes into sudden predictable and unpredictable behavior. So just as I told you, you see the next point is that it predicts the outcome. That means it describes the type of probabilities of different outcomes of measurements on quantum systems. And most importantly, it explains quantum phenomena. That means things which are going on in microscopic scales like superposition, entanglement, and most importantly quantum tunneling, where a lot of researches are going on. These things are being explained by quantum mechanics or by the entire model of the scientific theory of quantum mechanics. So now that we know it predicts the quantum system, it predicts the outcome and the quantum phenomena, so we come to the next question, that what is the nature of quantum mechanics? I mean to say, how does it behave, and what is the way that it actually behaves, and how things happen? Let us look into the next part of the video, what is called the nature of quantum mechanics. Now you see that when we started our classical understanding of the model, we saw something which is called a macroscopic scale. So the Newton's laws of motion, Galileo's law, Kepler's law, planetary motion, everything was defining things at a quite precise level at the macroscopic scale. Now, when we move from the macroscopic to microscopic scale, we should understand one thing, that it borrowed the same mathematical structure and philosophy from the classical system. Now, I know that what you're thinking, is it the same mathematical structure? Then why do quantum mechanics includes the linear algebra and complex functions? But I will come to that later. But what I'm trying to make you understand is that it borrowed the same mathematical structure. What do I mean by structure? Look into this. The foundation of quantum mechanics is very much classical in nature. I mean to say, when I say it is classical nature, I am not taking into consideration relativity. So that is why you see that the mathematics that you learn is also classical in nature. So that's indeed is a good news. So when we move from the macroscopic level to define the new scientific mathematical model of quantum physics, we borrowed the same mathematical structures because at the basic foundation quantum mechanics is very much classical in nature. I will explain to you what do I mean by classical in nature, and the mathematics should be also classical in nature. But here is a point of concern. As I have written, hold on. So the question is that, is there any difference between a classical and a quantum system? If I'm saying that it is borrowing the same mathematical structure, but again I'm saying that the nature of the classical maths is both of them same. So obviously the question is that, is there a difference between a classical system and a quantum system? Let us look into the next part of the video where we will try to define very easily what is a classical and a quantum system. So when we talk about classical system, we mean to say it is deterministic. That means the future state of a classical system can be predicted using mathematical formulation if you are given an initial state and you know where this state would lead to. For example, this pendulum. So an oscillating pendulum, if it goes to and fro and to and fro, so the point initial state when the pendulum starts moving, you know where it will exactly go. So that is why we call it deterministic. Also, you will see that classical system is continuous, and quantities like position and momentum can have any value if you are given a certain range. For example, this ball rolling down the hill. So the ball rolling down a hill or on a table can be anywhere on the table at any given time. So this concept of anywhere is something very central to classical physics. Also, as I have demonstrated earlier, that the pendulum moving to and fro, the momentum of a moving object can have any value within a certain range. And for example, if I consider velocity, the velocity of an object can have any value if you are given a specific range. This is what is typically defined, what is called a classical system. And here comes the most important part, that classical mechanics or classical system excels at describing the behavior of macroscopic objects. That means those which are very big, like planets, cars, baseballs, or things which we actually see in our daily life. So this is what we call as a classical system. Now hold on, I have told already that classical system and quantum system both borrows the same mathematical principles. I will come to that part later. Importantly, you see quantum mechanics is also probabilistic. That means we can only calculate the likelihood of throwing this dice up in the air. This person chance of pointing it at head, or this person chance of pointing it at tail. So we do not know its exact position or momentum, and we can say of a likelihood. This is very important. Quantized properties. Now we just saw, let me go back to the earlier part. So here you see I have told that it can be anywhere, it can carry any value and so on. And it defines things at a macroscopic level. But when we come to the microscopic level, we already saw that it shows the likelihood. And most importantly, this cannot have any value. So that is why it is called quantized. That means it can only exist in discrete packets. And these are called quanta. So think of the stairs. So you move from one stair to a second and a third, and these are very discrete. These are very discrete in nature. It cannot have any value, but it will have only discrete value. And obviously it happens in a very, very small scale. So quantum mechanics is crucial for understanding behaviors at this small scale. So automatically you might ask a question, so do you need to learn a totally different kind of mathematics, because this deals with something very quantized and very small and very probabilistic. So do you need to learn a totally different type of mathematics? And the good news is no, you don't need to learn a totally different mathematics. Let me justify this point in the next part of the video. So when we move from the classical to the from the macroscopic to the microscopic, the underlying mathematics is the same. So, and that is very good news. That means no extra headache, no extra learning, no extra things to get confused about, and you feel really relaxed. So the good news is that when you are learning the classical mathematics for a classical system, and the same classical mathematics more or less applies to quantum system. Now why do I use the word quantum system? Because of this. That is not entirely true, because this old person, Dr. Albert Einstein, changed everything that we look into the nature. So that is why I've written, with the effulgent dawn of relativity, the very landscape of physics was forever transformed. That means, although it is a good news that we don't need to learn much of mathematics, but it's a fact with the relativity coming up, we need to learn, because there are certain things which have changed. What are those things that have changed, and what are the new mathematics emerging? Let us look into the next part of the video. So here is the pendulum. So it actually signifies a classical system. So classical system has already generalized into special relativity, and this has also been generalized into general relativity. So till now we can say that general theory of relativity by far is more or less the accurate system of defining or measuring things at a macroscopic level. But here comes the quantum system, and we have divided this into two parts. So quantum mechanics is no more quantum mechanics. It has got a non-relativistic quantum mechanics, and it has got a relativistic quantum mechanics, which we call as quantum field theory. And the good news is that you can see I have just 1, 2, 3, 4. These are the thumbnails which I have shown, but you can find a lot of videos, and thanks to you, because you are making the videos quite popular, you can go and check out my videos in the live section, where I have taken live classes on the basics concepts of quantum field theory. And you can also check the videos which I have made, and the very recent one is the basic concepts of quantum field theory. And thank you very much for liking and viewing this video, because it is already crossing a good number of views. So in order to know more about relativistic quantum mechanics or the quantum field theory, go to Physics for Students, check out the lectures in the live section and the video section. I think you will feel happy. So we come back to our point. So now what we can tell is that non-relativistic and relativistic quantum mechanics, more or less, some of the mathematics is common in both. And most importantly, we are going to start today's learning in the non-relativistic quantum mechanics part, not the relativistic part. So the first thing is that what mathematics do you need to learn so that you can know both? That is a very pertinent question we are going to answer. Why linear algebra is important? Yes, we are going to look into that. And how linear algebra and quantum physics are related to each other, that is also something that we need to know. So this would give a push to our today's video, where linear algebra and quantum physics, the deep underlying mathematical and philosophical structure, we are going to know. But before that, what we need to know is that what is the mathematical prerequisites for learning quantum mechanics. When I say quantum mechanics, obviously I mean to say non-relativistic quantum mechanics, although some of this part, once you learn, it will be very clear in learning quantum field theory, that is the relativistic quantum mechanics. So first I would like to show you what are the mathematical prerequisites for non-relativistic quantum mechanics. So first part is linear algebra. And this would include vector spaces, linear transformation, inner product spaces, eigenvalues and eigenvectors, unitary and Hermitian operators. I'm not going to explain this because you already know that. The second most thing is complex number. Remember, I'm not talking of complex analysis. I will tell you why. So complex number would include complex number, functions, and complex variable, complex exponential, and all those things. Yes, now we come to know a little bit about complex analysis, which takes a step ahead with the complex number. Functional analysis, yes, functional analysis is something which would be required in order to know quantum mechanics deeper. Differential equations, ODE and PDEs, yes, solving linear ordinary differential equations, I mean to say boundary value problems. Then we move into partial differentials, PDEs, because understanding Schrodinger equation, separation and variables, eigenexpansion, these are important. Yes, probability theory, because probability, amplitude, random variable, statistical distribution, Gaussian distribution, all these things comes to be very, very important. And then obviously we can come to know a little bit about what is called a Fourier analysis. Now this actually is an kind of an overall idea, which is the mathematics, or rather I would say the concepts or the topics that you need to learn. But hold on, you don't need to learn all of them. Some of them are absolutely mandatory, and I'm going to highlight in the red box which of them are mandatory. Number one is linear algebra. You cannot learn quantum mechanics without learning linear algebra. Number two, complex number. Yes, because every phase and every eigenvectors and linear equations will have complex numbers. I have skipped complex analysis and functional analysis, and then obviously differential equations, it goes without saying. Probability theory, obviously yes, because everything depends on probability. So we come to the next, that is the relativistic quantum mechanics. What is the mathematics that we need to know? First of all, obviously advanced linear algebra, which it includes representation theory of group and algebra, tensor products and so on. Complex analysis, definitely it would be required. Advanced functional analysis, which would include distribution and generalized functions like Dirac delta function, Green's function, Sobolev spaces and so on. Yes, differential geometry, I won't say up to a very master's level, but manifolds and tangent spaces, Riemannian geometry, fiber bundles and connections, these comes into the play. Topology, some part of homotopy and homology, bundle theory, vector bundles, principal bundles, connections and curvature would be required. Group theory, yes, it is required because symmetries plays a vital role in quantum field theory. Group theory helps you to understand how physical laws remain the same under certain transformation. And this goes without saying. Special theory of relativity, because quantum field theory is an amalgamation of quantum mechanics, classical theory and special relativity. So you need to know about Lorentz transformation, Minkowski space and everything. Functional integrals, yes, because path integrals, foundation of quantum mechanics and quantum field theory, and you need to know measure theory because basic concept required understanding of functional integrals. And finally, some of the specific concepts of quantum field theory, which includes canonical quantization, Lagrangian and Hamiltonian, perturbation theory, gauge theory and renormalization group. Very important because we have to deal with the infinities. Now, among them, what are the things which are absolutely mandatory? Obviously, advanced linear algebra, then complex analysis, differential geometry for sure, special relativity, definitely functional analysis, and quantum field theory specific concepts. You can go to my videos, which is not very exhaustively mathematics, but you will come to know about the overall idea of what quantum field theory is all about. Now, having understood what are the mathematical prerequisites for relativistic and non-relativistic, we come to the next question, is that we are dealing with linear algebra, and that is what is the thumbnail of the video. So why quantum mechanics depends on linear algebra, or rather what is the underpinning truth of quantum mechanics or linear algebra as the fundamental tool for quantum mechanics, coming up into the next part of the video. First, definitely it would be the mathematical framework, and I'm going to elucidate on that mathematical framework which includes vectors and manipulations, etc. Most importantly, superposition and measurement of works, everything depends on linear algebra. So as I told you that this would be the first part, because there's a lot of fundamental concepts of linear algebra which I'm going to show, and you will now enjoy the learning linear algebra is not just learning the matrices, but something very deep to understand the physics. The second part would be, definitely it gives a picture of the quantum world, because if we consider something like an electron spin, we cannot consider as an arrow. So what do we consider? For example, a quantum state, and now it is not a vector space, it is a Hilbert space. So it will give you a picture of the quantum world. And here is what I was talking about, the big boy of quantum physics, that is superposition. So unlike everyday world, quantum things can be obviously in multiple state at once, and it is only linear algebra's beautiful mathematics which actually shows, by combining these things, how the blending is possible and how we can perform the mathematics on that. So superposition is important, and that is why we have to depend on linear algebra. The measurement gets clear. I will explain to that when we measure the measurements, or that is the observables and the operators, linear algebra cancels out the odd and we can get the possible outcome. Also, matrix representation, I think you already know, lot of matrix operation including multiplication, addition, subtraction, all these actually represent quantum states, and creation of new quantum state and operation of matrices is mandatory. And finally, what is called at the bra and kit notations. Dirac notation obviously is a concise and powerful way to know quantum mechanics, and that is not possible without linear algebra. So we can summarize now that linear algebra is absolutely an indispensable and mandatory in quantum mechanics. It will help you to understand the mathematical structure for predicting the behavior of the outcomes and making it as a foundation component of the theory and practice of quantum mechanics. Now, the first thing that I think it must be going in your mind that when we talk of linear algebra and quantum mechanics, the concept or the question is that why we call it linear in terms of linear algebra. So the first core concept one, which is coming up very important, is that what is linearity and how it is related to quantum mechanics. Coming up into the next part of the video, linearity and quantum mechanics. So first we will understand why we call linear algebra as linear. Obviously we just cannot skip those things and keep on doing the mathematics. So it comes from the Latin word linea or linearis, and this is an adjective which actually shows that something which changes or progresses straight from one point to another, one stage to another, and it has a starting point and an ending point. We can also say that something linear is like a line. And when we close our eyes and when we see a line, what do we see? It is an adjective and refers something that follows an expected order of sequence. Remember, it is showing an expected order of sequence. And linear movement or force occurs in a straight line rather than in a curve. So we understand that linear is something which has got a starting and an ending point, one stage to another, and most importantly, an expected order or sequence. Now, when we talk of quantum mechanics, remember that we just have defined quantum mechanics telling that it's got a discrete values of energy, isn't it? So classical physics was what it has, can any value, but quantum mechanics can have discrete value. That means it is quantized. And that actually justifies linearity and quantum mechanics are related to each other. Why? Because linearity is expected, so is an expected sequence, a starting and an ending point, a line which has got a stage from one to another. And indeed, quantum mechanics is also something which is resembling that, because it has got an expected, quantized and discrete energy. So that is something amazing. I was really excited to discover, and while I was reading that, I thought to convey this to my dear subscribers, that when you're learning linear algebra, first understand why it is called linear. Obviously the scenario becomes very clear that quantum mechanics talks about discrete, expected, quantized energy, and linearity philosophically also follows an expected sequence. So having established that, we find that linear algebra actually deals with vector spaces and linear transformation, and you see I have written it in red. The resulting transformation also behaves proportionally. This proportionality is something which we now see that when we scale a vector, so v and v get scaled into 2v. So what do we say? So for any vectors u and v, and we get a linear transformation t, the additivity property states that t within braces u plus v equals to tu plus tv. And for any vectors u and a scalar c, the homogeneity property states that t within braces c multiplied by u obviously would be equal to ct within braces u. So we see that the additive property, the homogeneity property, a lot of other properties which I have skipped to make the video crisp, these are all related to linear algebra, and they're very linear and they behave proportionally. Now you might ask a question that how does it relate to quantum mechanics? Because these are all properties to linear algebra. In the next part of the video, I'm going to give you a very simple example, and I will show you how this property is related to quantum mechanics. Now you already know that quantum states can exist in superposition. So if I take a quantum state psi1 and psi2, and I consider these are valid. Valid means these are mathematically valid, and we have experimentally validated that. So I call it as valid quantum state. So if psi1 and psi2 are valid quantum states, then any linear combination, I have just taken A and B to make you understand, but it can be anything. Any linear combination, that is A psi1 plus B psi2, is also a valid quantum state. Definitely. And that actually comes up here, that a quantum system can exist in multiple states simultaneously, unlike a classical system where it has a definite discrete state. I should not use discrete, but a definite state. So if I now take C0 and C1 as complex numbers, because you all know why we use complex numbers in quantum physics, we get this one. that is psi with a bra and a ket notation, C00 plus C11. And this bra proportion of psi, what is that? It is a quantum state. C0 and C1, these are complex numbers. So we can say this has got a weighted by the two probability amplitudes, and 0 and 1 are what? These are particular solutions to an equation. Simple. So as soon as we understand that linearity is something inherent to quantum mechanics, and if we combine two valid quantum states, we get another valid quantum state. So any linear combination of two quantum states leads into another quantum state. And that is why linearity and quantum mechanics, or I would say linear algebra and quantum physics, is related to each other. So here you see that the property or the properties of linear algebra is a nice way to measure the characteristics. And this brings us to this funny picture, whether it is the chicken or the egg scenario. So if I consider linear algebra to be the effect, so is it that the quantum mechanics is the cause? Or if quantum mechanics is the cause, then is linear algebra is kind of an effect? So which one is earlier? Please do let me know in the comment section of Physics for Students if you are watching this video, and you can answer this question, which one would be the cause and which one would be the effect. So overall, from here we can say that in order to measure the outcome, whatever it shows in quantum physics, we need a tool, and that is only linear algebra. And linear algebra, as the name goes, is linear in nature, and the mathematical structure of quantum mechanics, from its governing equation that we will see soon to the way physical properties are represented, is inherently linear. And this linearity actually allows superposition, the ability to have probabilistic combination. And from here we can also say that mathematical representation of linearity results into what is called superposition. We will explain later in some part of the video. Now this is how beautifully quantum mechanics and linear algebra is related. And this brings to me a very philosophical question, is that is nature at the microscopic level inherently linear? Does the grand symphony of existence truly follow a linear score at its fundamental level? Quantum mechanics throws a wrench into his classical assumption. Particles defy our intuition, existing in blurry superposition of states, and probabilities reign supreme. Perhaps linearity is just a comfortable illusion, a framework we have built to understand the macroscopic world. Yet a nagging question persists. Could these equations, could these quantum phenomena be emergent properties arising from some deeper, unseen linearity? The universe in its grand design might have held both these seemingly contradictory aspects, leaving us with the humbling realization that our grasp on reality itself might be inherently limited. Whatever you feel about this philosophical question, let me know into the comment section. And this brings another important question which we are all physicists are striving to achieve, is that can quantum mechanics and general relativity be merged into one theory of everything? Well, if you take my opinion, I would say it is difficult, and there's a big question. The reason is not because of the mathematics. The reason is that quantum mechanics shows inherent linearity, and general theory of relativity shows its inherent non-linear nature. Coming to the next core concept, that is linearity and Schrodinger equation, because this is the core equation which guides and which is the pivotal force of quantum physics. Let us look how linearity, linear algebra and Schrodinger equation are related, coming up into the next part of the video. So the Schrodinger equation, as you know, is a very fundamental equation. It actually shows how our quantum system evolves. And you can say it is like a Newton's law of motion which actually guides everything in the quantum world. We are not going to explain Schrodinger equation in this video, but remember that this is a partial differential equation. That means wave function depends both on space and time. And it is a linear equation. That means if you have two solutions, wave functions that satisfy it, then any combination of those solutions is also a solution. This is important. So if we take a Schrodinger equation for a single non-relativistic particle in one dimension, it looks like this. But hold on, we are not going to look into this complex equation. I'm going to make things simple. This is a stationary Schrodinger equation. Why I have taken a stationary equation? Because number one, energy of the system remains constant, and mathematically the wave function does not depend on time. That is, del psi by del t will be equal to 0. It will be easier to, I would say, calculate. So from this equation, we can write this equation. And here you can see psi double hash is nothing but the second order derivative, and this entire equation is a homogeneous linear ordinary differential equation of second order. What do I mean by that? I mean to say that the solution of psi x have some properties. And this will show you that how linear algebra and Schrodinger equation and linearity is related. And what are they? This is what if psi 1x and psi 2x are solutions to this equation, and if a and b, whatever, a, b, alpha, beta, you can consider anything, are constant, then we can say that psi x equals to a psi 1x and b psi 2. That means I have just substituted the constants over here, and this is also a solution to this one, the earlier one. So what we deduce from here is that the core equation, which was talking that the core equation governing quantum system, that is the Schrodinger equation, is a linear partial differential equation, which will also result a solution to this. So psi 1 x1t and psi 2 x2t are solutions. If they are solution, then I can combine anything and I can get this also as a solution. And this is something which is remarkable. So remember that we are not considering the relativistic Schrodinger equation or the Dirac or the Klein-Gordon equation, just taking the classical equation. So if this is a solution, then any linear combination would be a solution. So if I take now the non-relativistic single particle in one dimension, then if this one is a solution, then this is also a solution where these are constants. And from here we get a wonderful idea that superposition allows a quantum system to exist in multiple states simultaneously. And these states combine linearly to form a new valid state. So, and this would not be possible if the underlying framework was linear, and that is why we need linear algebra in order to understand the underlying framework which is very linear. Let me give you a very rudimentary and a layman's approach to an analogy. Now suppose that you are preparing your birthday cake and you have got a recipe which is psi 1 and a recipe which is psi 2, and both of them makes a wonderful cake. Now you want to add some ingredients like some carrot or your capsicum and some chocolate and cheese, and you call this as ingredient A and ingredient B. And these two ingredients can be combined into a single equation which can also form a fresh new cake. So you can also make a perfectly valid cake by mixing these two recipes together. And that is the reason you will see that the Zeilinger, Anton Zeilinger and others in the world of quantum physics further, we are now creating superposition in order to maintain and in order to safely secure what is called the cryptocurrency or the transaction. So obviously A and B would be complex numbers corresponding to the recipe, and in quantum mechanics complex numbers are used because they encode both the magnitude, that means the amount, and the phase, that is a property related to wave behavior, which is called the phase of a wave, you already know. So from here what we say is that the mathematics of the mathematical structure of the quantum mechanics, from its governing equation, that is Schrodinger equation, to the physical properties, are represented as inherently linear. And this linearity allows superposition, the ability to having probabilistic combination of states, which is a cornerstone of physics. So till now this establishes why we need linear algebra and linearity and the deep underlying I would say concept of quantum physics, which is linearity. Obviously the question now comes to your mind that what are the concepts in linear algebra that you need to know? Is it that you need to know all the concepts, etc.? Let us look into the next part of the video. What are the concepts in linear algebra that you need to learn? First, you need to learn about vector spaces and what is called states. So if you want to find out the position and momentum of an electron or any subatomic particle, we cannot mention those by arrows as we do in classical physics. So vectors in linear algebra, vector spaces, are something which are called Hilbert spaces and which exist in n-dimension complex structure, which I have explained in my earlier videos in quantum physics. So in quantum mechanics, the state of a system like electron's position is described by a vector in a complex vector space. So all those arrows or those we mention in classical physics, vector mechanics or vector calculus, the same happens here in complex vector space. So that is why it is important. So why? Because if we get a state vector psi, that means, for example, an arrow which has got a position, a momentum, and it expresses in a Hilbert space, for example, a vector space, which is similar to classical physics, we get something like this. And quantum states that are represented as vectors in Hilbert spaces are denoted by a ket. This is one. So it is very central. In order to determine anything, position, momentum, etc., what we need is a vector space, and we need a Hilbert space, and that is why vector space and states are important. The next thing which is important is that we talked about the arrows, etc., is called an inner product. This is too important, even important more than classical physics. So inner product is basically multiplying the two vectors. I'm going to say in this case the two quantum sets. So for vectors this and this, psi and phi in a Hilbert space, we can say that the inner product is something like this. Don't worry if you don't understand the mathematical notation, just understand the underlying meaning. Why it is important? The importance is that quantum states are represented by vectors in complex Hilbert spaces, which is denoted by psi. So if I get an inner product between these two vectors, two state vectors psi and phi, it gives a complex number. That means it actually shows or quantifies the overlapping or similarity between two states. When a set overlaps another, what we get? We get an overlapping understanding, like the similarity between the states. So this overlap actually helps to understand interference pattern and a lot of other things. What are those other things which inner product and the overlapping denotes? Let's look into this next part of the video. So inner product between two states, this and this, indicates the probability of the system transitioning from one state to another. That means how a state, quantum state, transits from one to another, that is being measured through inner product. So and we obviously using the Bond's rule, if we square it, we get the actual probability. But we are not concerned about the actual probability. The inner product is important in quantum mechanics. First, it allows to calculate probability. That means how likely a system will be. Second, as I told you, overlapping means that a large inner product signifies that they share some common characteristics. It's just like a Venn diagram which is overlapping. And third is that, which is a little bit technical, that we can express the complex states by decomposing into simpler states. So that is why this is super important. So inner product, I can tell you with an analogy that imagine that you're navigating a fog-laden landscape like this, where landmarks are bloody and directions are uncertain. So the inner product in quantum mechanics acts like a special compass, and it allows to measure the overlap between blurry quantum states. This overlap tells the probability of finding a particle in a specific state, like a spin up or a spin down. So by understanding the inner products, we can navigate through this fog-laden landscape and calculate the measurement outcomes, and it unveils the hidden connections between seemingly different states or seemingly different landscape, a crucial skill for unlocking the mysteries of the microscopic realm. Now you see that there are other concepts of linear algebra like operators, eigenvalues, unitary operators, tensor product, diagonalization in matrices, a lot of matrix operation, commutators, Fourier transform, linear transformation, but all these things we would be dealing with the next part of the video because we cannot deal those in one video. But now we come to the most crucial, important and the fundamental idea that what are the books or what are the linear algebra books which are there, and what is the best book for you to understand quantum physics. First, I would say you can pick up a basic understanding of the linear algebra. Gilbert Strang books is phenomenal. This book is a little bit advanced, and Sir Glang's books is also. So first, in order to understand the basics of linear algebra, I would say all these books are very good. Coming to the quantum mechanics for linear algebra for quantum theory, you can pick up this Per Olof Lodin's book, which is purpose is basically to essentially it contains the mathematical tools. So it contains set theory, linear spaces, binary product spaces, so on. There are a lot of chapter and problems on sets, and the target audience is advanced graduate and undergraduate students in computational chemistry and physics. So but I found that book very good. Here are the content of the book. It starts with the elementary set theory, linear spaces, binary product spaces, and so on. The books has got a lot of examples so you can understand what is the linear space, binary product spaces, and so on. So remember that this is something which is very precise only toward the linear algebra. The second book would be this one, John David Jackson, and the quantum and the Amazon rating is quite high, 67%, and this is Professor John David Jackson. This is called the Mathematics for Quantum Mechanics, and it contains everything. As you can see that it starts with the eigenvalue problems in classical physics, orthogonal functions, Fourier series, and then go into linear vector spaces and so on. So it is not only for linear algebra, but it comprises a lot of things. Now, other than these two books, it is difficult to find a specific linear algebra book for quantum physics. But this material online, I have put up a description in the description box, the link. This is for Galileo Physics Virginia Edu classes. And this is a very good literature and a very good website which is precise to linear algebra for quantum mechanics. You can go through that. The description, the link is given in the description box. Also, this particular website is specifically again linear algebra for quantum physics. You can go through it and learn it. So because there are not much of videos and literature into that, it motivates me to make more and more videos on linear algebra for quantum physics, and I think that I would be continuing with the part 2 of this video. So I'm immensely thankful for those who have watched it. Here is a quick summary. We learned what is quantum mechanics. We learned the nature of quantum mechanics, relativistic, non-relativistic, mathematics that is required. Most importantly, the connection between linear algebra and quantum physics, the linearity and quantum mechanics. Will we ever be able to find out a theory of everything, linearity and Schrodinger equation? What are the concepts and what are the suggested books on linear algebra? This is a quick summary on what we learned in today's video. Thank you very much for watching today's video. For those who have taken up time and watched my video, please do subscribe to my channel Physics for Students and click on the bell icon and click on all to get all the notification from Physics for Students. You can write to this email ID and you can like and subscribe to my other channel where I put up videos only related to general theory of relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will keep you surprising with more and more interesting, fun-loving and beautiful videos on physics, mathematics and career counseling on how to attend interview questions and so on. But till then, goodbye and may the good Lord be with you.